Welcome. This is the second video on I2C. In this video I'll be talking about the I2C Core. Remember, you can get this VERILOG code, the full project tutorial and instruction, LOGISM, circuits, everything about this project free from projectfpga.com/I2C to get the full project documents. So in this tutorial I'll be using the LOGISM circuit to talk about the core. So in this tutorial, remember last time we talked about the two state machines, the SCL main state, which is this one, which is this one, SCL main state, and the SCL state. I told you that this main state works for both when the I2C is operating as a master or slave, while this works only when it's operating as a master. So I'm going to talk about this. We're going to talk about this. So let me highlight it. Excuse me. I want to talk about this particular section. This section is being controlled by the SCL state. Sorry, bad for drawing. So this is being controlled by the SCL state. So that is when it's operating as a master. This is a very crucial part of it. I'm going to show you why. Excuse me, I'll show you why. So watch closely and you can see that this SCL state controls all the multiplexer that goes into all these flip-flops. I'll highlight it again so you see. So this is it. Let me highlight it. You can see that this SCL state controls all the multiplexer that works for all these different outputs here. This one, all these ones to the end. So this SCL state controls all the multiplexers. This multiplexer, this one. Let's go up. And all these multiplexers, this one inclusive. So it shows that is basically what the SCL state does. So let's talk about these signals and what they are. So the SCL out is, remember I told you that the SDA and the SEL, we are told that they are just two signal lines using I2C. But the internal circuitry has SCL in, SCL out, SDA in, SDA out, because they are bidirectional. And they're actually open drain, but that's why different. You can read up the open drain on the website or from Foolish Engineer YouTube channel as I instructed. It's very important to understand because the open drain is the major differing or something that makes I2C very unique from UART and SPI. So you need to understand what it means by open drain. I explained it on my website, or you can use Foolish Engineer to understand it more also. Then remember again this SCL out. SCL out means the output, the SCL output. So they also have the SCL in. So this is the SDA out, which is the SDA output, the data line output. Stop SCL is used to halt the SCL, that is, it is used to set the SCL line high or low. So then again we have clock count enable. Remember when we are talking about this counter, let me show you the counter. So this signal, called counter enable signal, is going to be fed here. Sorry, this is a counter. When we'll be doing the top level, it's going to be fed here. This is the enable. So it is what enables the counting. So that's why it's called. Remember, we have the load also and the enable. But the one we just saw now, the clock count enable, which is which is this one, will be fed there. We use it for counting. Counting is different from bit count. So you have the clock count reset. To reset the counter, it's going to be fed to the load bit there. We have the arbitration reset. Arbitration is a principle, an operation in I2C. That is where two or more masters is trying to operate at the same time. You can watch Fish Engineer's video on it. Is very explanatory. So the slave with lesser address is going to take priority. I can explain it to you personally if you are finding it hard to understand. Then you also have this interrupt reset. Interrupt is likewise generated after every transmission. I'm going to show you how the interrupt is being generated. But let's discuss these signals one after the other. Let's just talk about this one. How the SCL main state controls this. So we're going to discuss this SZA line, SCL at the same time. Let's talk about the two of them, the SCL and the SZA line together. So initially at the idle state, we are told that the SZA line is high, that is 1 in the idle state, and then for us to detect the start condition, for the start condition to start, this condition has to be met, the prescale register and the clock count. We are going to talk about the prescale register when I'll be talking about this sub-circuit, the controller interface, but it doesn't really do much here. But just know that whenever this condition is met, that is when the master will generate the start signal. And what happens, how does the start signal occur? Whenever the SZA line is low, while the SCL is whenever the SCL line is low while the SCL line is high, the start signal is being generated. So as you can see, this state on the third state machine, this just note that each part of this multiplexer means when SCL state is 1, 2, 3, 4, 5, 6, 7. So that is what happens here. So let's watch how this SDR signal actually transmits bits. After the initial state when it's high, the next bit it sends is, it first of all sends a low bit, then it lashes it here, then the next one it sends a 1 and a 0. So this is more like a start bit pattern. A 1, next a 0, then next a 0 because it lashed it, then a 1 and a 0. So at a point when it sends a 1 and the SCL line is low, that is 0, that is when the start condition occurs, and that is on this fourth line when it sends a 1, and check here, the fourth line it sends a 0. So that is the condition where the start condition occurs. So that is where the point where the start condition occurs, and after that it goes low. It either goes low or it starts sending the output. So this is the master SDA. The master SDA is the data output which is going to be sent out. Go to the code, you see all these things. So it either sends a 1 or a 0, or it sends the SDA line output. That is, see what is controlling it, this. So whenever it's met, it starts sending the master SDA output. So this is how the master starts the start condition. So the stop SCL, when does it stop when does it raise it high? Now watch, the first three conditions are low, it does nothing. Now let's see how it goes high. So this is where it goes high on the fourth line. So this is the condition for it. All these conditions must be met. That is the SCL main state, no longer the SCL state. It must not be 2, 5 or 6. 2, 5 or 6 are non-transmission states. These states are when it sends the acknowledgement. At this state, is expected to send acknowledgement at 2, 5 and 6. Remember, 3 and 4 are for transmission and reception. So at the end of every transmission and reception, it goes to either state 5 or state 6. Whenever it goes to either of these states, it sends an acknowledgement. So that is why this bit here is here 1. So long as it's not in any of these states, keep this stop SCL low. Then clock count enable. Have the clock count enable, clock count reset. So the two are for the clocking. So you can see how it goes when it sets it to 1 and when it sets it to 0. Then again, so you can see it's being controlled from this SCL state. As usual, these three lines are for the clock reset and call reset, clock and reset or H reset. So please, let's likewise take note of that also. I think I did well to explain this. In the next tutorial, we'll be talking about we're going to talk about this. This is more like the other part of the state machine, other part of the core. We'll discuss what it does and how to use them. Thank you.